And we're live.
All right, cool. All right, so this is for all the people that are down playing in Southern California right now. So hope you're having fun. So do the cues, how we doing? So last time, what were we looking at? Do you remember?
Equilibrium.
So equilibrium. What kind of? What was the name for those differential equations?
Autonomous.
Yeah. So those were the autonomous differential equations. So those are ones that were y prime equals a function of y. So we saw that those were always separable, right? You just went over that function and then integrate. But what we really looked at there were equilibria, trying to figure out where we have kind of those static places. And then if we were to move away from them, do we come back? Do we go away? So we classified equilibria as stable versus unstable versus semi-stable, and all that sort of stuff. All right. So any questions on any of those? And I know I promised that we were going to have a quiz on linear first order today, but the printer is not working for me, so we're not having that quiz today. So anyway, we might not end up doing one for linear. Well, I'll let you know at the end of today what we're going to do later this week. But, all right, so then we're going to turn our attention to another kind of differential equation. All right, this is another one whose solutions are well known, and these are called exact. Let's start there. All right, now exact differential equations have a very specific form, and they look like this. So if you can write it in this form, this is what's considered an exact differential equation. Now, these are not necessarily linear. The way to read this, like this guy m, notice that it's a function of x and y. So it's a multivariable function. It can have x's, it can have y's, linear, nonlinear, doesn't really matter. There's another similar function of x and y, and this one's being multiplied to y prime. So really the way to think about this is an exact differential equation is going to be one that we can split into two pieces. There's the stuff times y prime, and the stuff that's being multiplied, or not being multiplied to y prime. Okay, now, this isn't enough for it to be exact. There has to be something special about m and n. I don't want to tell you just yet. Okay, we're going to just kind of hold on to that for a second, like what needs to happen with m and n for them to be exact. Because, for example, any linear first order can be written in this form, right? Like, think about when we do a linear first order. It's, what do they look like in general? Okay, good. That's a great place to start there, right? So y prime plus
Y.
So some function, right? P of t times y equals q of t. And I just want you to notice that this can be rewritten in the form that I've got here with the m plus n. So it'd be p of t times y minus g of t plus y prime equals 0. And in this context, the p of t times y minus g of t, that's m. And then n would be 1. So that's how we're going to read these things, like whatever it is, right? Obviously, when you're first order, it looks like this, but it's basically whatever we're multiplying to y prime, that's n. And then whatever else we're adding, that's n. So, like, in reality, every first order differential equation can be written this way. You can do the algebra to write it like this. So that's not enough to make it exact. There's got to be something else to it. Okay. So when we're in this form, let me show you an example of one that is exact, so that we can kind of figure out what it is that makes it so that we can kind of go backwards. Right? So here's this example. So suppose that we've got this guy, 2x plus y squared, that's going to be the one piece, plus 2xy times y prime equals 0. So this one is exact, just so you know. This one is exact. But let's start by just looking at what m and n are, get kind of used to doing those. So m is going to be 2x plus y squared, and then n is going to be 2xy. So, are you good with how you're going to read these? What's m and what's n? All right, now what makes this exact is something special about m and n. There's something really special about them. And I want to remind you about something you saw back in, probably would have been fourth quarter in vector calc. It might have been in third quarter, I'm not exactly sure. So you remember something with partial derivatives with my and x kind of stuff, right? Well, think about this. What if I took this guy right here and I just rewrote it real quick with the dy and dx. So we've got m plus n times dy dx equals 0. I'll multiply by the dx. So we get it kind of turned into that form. Do you recognize that?
Yes.
I'm seeing some head nods. But what was that?
Count 4.
Okay, so somewhere back in like October of this year. Do you remember where that came from?
No. It's one of the theorems.
Oh yes, it shows up in one of those lovely theorems, right? Stokes and Greens and all those guys. Okay, so you recognize it there. All right. It turns out that if this guy m is a partial derivative of something with respect to x, and n is the partial derivative with respect to y, so this is an if, then the integral of m dx plus n dy, so that's the fx dx plus fy dy, that just equals big F. This thing's called the potential function. That might help ring some bells there in your brain. But you use that sort of stuff when you're finding level curves, gradients, all that kind of stuff. And yes, it does get involved in some of those lovely theorems when you're trying to do line integrals and stuff like that. Okay, so if this is such, then integrating on the left-hand side of this form is just going to give us that potential function. I remember the whole goal with differential equations is to get rid of the differentials, which means integrating, and we're going to be able to do that. All right, so look at the one that I gave you. I already told you that this is exact, so you know I'm not going to ask, is this the partial of something with respect to x and this the partial with respect to y the same thing. Let's instead remind ourselves how we do that. So if we want to find this function, what we have to do is integrate each of these pieces separately, which means I need to integrate m with respect to x. Now, the 2x part, we treat that just like always. Integrating that's going to give us an x squared. But then what does the y squared give us if we integrate with respect to x? it's xy squared. If we differentiate, it goes to 0. But yeah, Haley's exactly right. It's going to give us some x times y squared, because y squared is constant with respect to x. Oh, and speaking of constants, we need to add one now. But I don't know if you remember this. But that constant is a constant with respect to x. So it could be something like e to the x. It could be x squared plus 2. Oh, sorry, not constant with respect to x, constant with respect to y. Because if that thing's only made of y's, when you differentiate with respect to x, it goes away. So whatever this potential function is for this exact differential equation, it will have x squared. It will also have xy squared, but it could potentially have more. It could have other things that are just involved in y. All right, so then what we do is we do the same thing, but for the other piece. We take that 2xy, and we're going to integrate with respect to y. So the 2 and the x are constants. The y gets us a y squared over 2. So when we integrate that, the over 2 cancels, and so we're left with xy squared. But now there's potentially something that's just made out of x's. Okay, so I think I'm starting to see definitely some recognition. You guys are kind of going, oh yeah, I kind of remember doing this. So if we put this together, then big F, well, it's got to have an x squared, and it's got to have an xy squared. I always just go to the first one and take all those pieces and put them in. Then I go to the next part, and I put in any pieces that I'm missing. Well, this has an xy squared. It's already there. And so there it is. There is a function whose partial with respect to x is 2x plus y squared, and whose partial with respect to y is 2xy. Okay, so this is why this one's exact, because these m and n are such that we can find this potential function. All right, now, this has not solved the differential equation yet. There's still a little bit more to it. All this is the integral of the left-hand side. So now we need to integrate 0. Well, what do you get when you integrate 0? A constant. Okay, so the solution to this differential equation then is now x squared plus xy squared equals c. That's what we can put into our box. And there's the implicit form of the solution to that differential equation. All right, so really all this is, when we talk about exact differential equations, these are just the ones that are the results of doing the partials. So given any function, if you find the gradient and put those pieces in here, you've created an exact differential equation. The harder question is going to be, how do you look at this and go, oh yeah, that's exact? That's really what the question needs to be. Is now that we've seen what we do, it's just a matter of integrating with respect to x, integrating with respect to y, and then kind of match them up. The next real question then is, how do you tell? All right. Before I get there, though, are you guys good with how to do this? Like if you're given one? Yeah, Jackson.
For making it f of x and y, do you just add, because they both have xy squared, and then one of them has x squared?
Yes.
You just
I just combine it. So remember this guy? This one said I could have xy squared, and then I could have any other x's that I could possibly want. Right? Okay, well, how about we just make that x squared? because my first thing needs an x squared, right?
Right.
So basically, what I do is I just go, okay, I need an x squared. X squared, x squared. I need an xy squared. Xy squared, xy squared. Now, can there be more stuff? Sure. Let's see if there's more stuff. So I run over to the other part, and I go, all right, I need an xy squared. Yeah, it's already in there. Not going to duplicate my effort.
Yeah.
Okay, and then I could have more stuff that's just x's. Okay, well, yeah, I already have those more stuff that are just x's. So it's literally, I just put it in the pieces until I run out of pieces.
Sweet.
All right, so now that this is kind of reminding you a little bit about this, do you remember, because like think back to vector calc when this was showing up in those theorems, right? Let's not be too concerned about which one it was. But when you were doing this, there was something special about these to get, because this is what's called a conservative vector field. Conservative vector fields are the ones that have a potential function. That's really where you first started seeing this. Was here's a vector field, is it conservative? Because if it's conservative, then you have lovely things you can do, right? Like if you got a line integral, fundamental theorem, you can just go one point and the end point, either end, what do you get? Look at the difference. You don't have to worry about path. If it's a closed integral over a closed path, conservative gave you 0. Okay. There's a bunch of stuff that you saw back in October, November. If you don't remember it, that's fine. But that was the context of this. All right, so does anybody remember what the relationship had to be between these two for your field to be conservative?
Yeah.
What was it?
The first one, the partial with respect to x, if you differentiate with respect to y, and then you differentiate the other one with respect to x, then they should be the same.
Okay, and that's exactly it. This was the check for conservative vector fields, is if you got your m and your n, if the derivative with respect to y of the first one was equal to the derivative with respect to x of the second one, then you knew it was conservative and you knew there was a potential function. Well, guess what, folks? That's our check for these. So let me erase this and put down what actually has to happen for this to be exact. Right? These have to be such that my equals nx. So if this is the case, then the solution is going to be f of xy equals c, where that big F here, this is the potential function. So exact differential equations are the results of vector fields. They're the differential equations that come from vector fields from back in the day. All right, so this is literally all we're going to have to do. We're going to make sure that they're exact. Just check this real fast. Once they're exact, we'll find the potential function, and then we'll set it equal to c. And heaven forbid, it's an initial value problem. And then we have the one more step once we're there of plugging in. So let's do a few more. Let's do a couple more examples here. And of course, then I'm going to show you the twist, because there's always a twist, you know that, right? But let's just do a few more so you can kind of see how this plays out. So let's try this guy. Let's say we've got 3y cubed e to the 3xy minus 1. We're going to add to that 2y e to the 3xy plus 3x squared 3xy squared e to the 3xy times y prime equals 0. So I know it looks scary, but let's just see how it pans out. So here is m. So let's start by finding my. Find the partial with respect to y. All right, so what's my? Crap, you have to remember all your derivative stuff. So this is product rule. We got to use product rule here because we've got 3y cubed times e to the 3xy. So I'm going to get 9y squared e to the 3xy plus 27xy cubed times e to the 3xy. X's are constants in this case, right? So derivative of the first bit is 9y squared times that. And then we get the 3y cubed times the derivative of this, which is going to be 3x times e to the 3xy. So I put that 3x in there. Okay, so there's my. Now n is this guy. And now let's see if we can find nx. Okay, well here the 2y is a constant. The 3y is also a constant, so when I differentiate that, I'm going to get 6y squared e to the 3xy. The other piece is going to be product rule. So I'm going to get 3y squared e to the 3xy.
I don't think you're done with the first part now. You have to product rule that one too, yeah.
I absolutely do not. It's just x. X is my only variable.
You have 2y times, oh wait, you're different.
The 2y is constant.
My bad.
Yep. But thanks for checking on me. So here though, with respect to x, the derivative of the first bit is 3y squared times the e. And then I'm going to get 3xy squared times the derivative of this with respect to x, which is going to give me another 3y. So I'm going to get, something's off. Oh, I know where it is. 9xy cubed e to the 3xy. 3 times 3 is 9. Not 27. All right, so if I put this stuff together, those first two I can combine, get 9y squared e to the 3xy plus 9xy cubed e to the 3xy. And notice that those guys match. So I know that this is now an exact differential equation, which means I can find a potential function, and once I find that potential function, I just set it equal to c. All right, well, let's find that potential function. But before I go there, you guys okay with those partials? I apologize for that 27. 3 times 3 is 9. 3 cubed is 27. All right, so here we go. I'm going to now find my potential function. So I'm going to start by integrating this first piece, bless you, with respect to x. So I'm going to start there. All right, so that 3y cubed is a constant, just stays there. E to the 3xy is going to give me an e to the 3xy divided by 3y. Because that 3y is constant. and then I subtract, what? What's the integral of 1?
X.
It's just x. Okay, and then I'm going to put, but then there's some potentially constant function of y. So for sure, it's going to have this stuff in it, but it might have more. And if it has more, it's just y stuff. So let me reduce this a little bit. It gives me y squared e to the 3xy minus x. All right. So now we have to integrate n with respect to y. So now we're going to do this. That's the integral of 2y e to the 3xy plus 3xy squared e to the 3xy dy. And this is when you die a little bit inside. Because like think about that first piece, the 2y e to the 3xy. If we're going to integrate that by hand, what method do you have to use?
Integration by parts.
It's integration by parts, because we've got multiplication, y times other stuff. What do you have to use for the other one? Integration by parts. Okay, so this one requires integration by parts twice. Do me a favor real fast. Differentiate this with respect to y. And when I say this, just in case people watching aren't sure. Look at this piece. What happens if you differentiate that with respect to y? We do product rule, right? So we're going to get a 2y times e to the 3xy. 2y e to the 3xy. This one, when I differentiate with respect to y, I'm going to get a 3x e to the 3xy times this. So I'm going to get 3xy squared e to the 3xy. All right, so it turns out that this which is y squared e to the 3xy, plus your favorite constant function of y. Now, I showed you this one just as a way to help you out, because sometimes these integrals are horrible. So what I like to do is look at where I ended up with from the first one, look at what its derivative is, and if it matches, I'm done. If it doesn't match, I'm most likely off by just whatever this constant of y is, and I can just throw that in and be done with it as well. So sometimes you don't actually have to do both integrals. Sometimes. All right, well, regardless, we now have our function. We're going to have y squared e to the 3xy minus x, right? I need both of those pieces. I go to the other one, I need the same thing. That y squared e to the 3xy, I already got it. So then we'll just set that equal to c. And there you go. There is the solution to that big, horrible, ugly-looking differential equation. It is a similarly ugly-ish implicit form, but we got it. All right, so I'm going to give you one more here, and I want you to do this one on your own. Okay, try this one on your own on your paper. See how far you can get, and then after you give it a go for a couple of minutes, I will walk you through the solution. So try this one out for size. Let's go with a 2ty over t squared plus 1 minus 2t. And then we're going to subtract from that 2 minus the natural log of t squared plus 1 times y prime, set that equals 0. But I'm going to make this an initial value problem as well. We'll throw on that one extra step. So we're going to have y of 5 equals 0. Okay, so before you jump in and just try to find a potential function, first confirm that the potential function exists. It's actually pretty quick check here. All right. Confirm that that exists, then find your potential function. And I'll just kind of float around. I'll look over your shoulder, make you nervous. So for those of you watching the video, it's going to be kind of boring here for a little bit. Okay, more boring than it's been. Someone calling you about your extended warranty?
Yes. That's exactly what was happening. So.
There's a little bit more on why. Alright, so you don't actually have to do a quotient or anything like that. Just think about all this stuff is being multiplied to y's and 2t over t squared plus 1. All of that.
Okay.
So my is 2t over t squared plus 1. Oh yeah, that was nice and easy. So this guy, you don't want to make your focus on y. You differentiate with respect to y, you check it. Unfortunately, it's not that high. It's not terrible, it's not that.
Forgetting. Isn't this a true one?
Nope, that's not a trig one. The y is constant, so it's just going to stay there,
I get it.
right? And then you've got 2t over t squared plus 1. When you have fractions, look for, if the top is the derivative of the bottom, good things happen. And possibly, I don't know. I think so.
Sick.
Looks pretty good.
I guess I could double check the history of class one.
For this one, is you sub an idea?
Oh yeah, 100%.
Yeah.
Yeah, because your du is 2t, which is on top.
Okay.
So it's like having y over u.
Okay.
T squared plus 1. Yeah. Cool.
All right, so what's the hard part here? Remember how to do all the integrals, right? I mean, you do, but you don't.
You just do that one and then do that one.
Yeah. All right, so let's kind of put this together up here. So let's start by checking this. So if I do start with, this is m, right? So let's look at my. In terms of y, all of this 2t over t squared plus 1 is constant. So you get that times the derivative of y, which is 1. And then the 2t is also constant, being added, so that goes away. So there's my my. If I go to nt, right? If you just differentiate this, you're going to get a minus 2t over t squared plus 1, because the 2 is constant. The minus sign carries down, and then natural log of stuff, its derivative is just the stuff on the bottom and the derivative of the stuff on top. But notice that that's not equal. But that's because of this minus sign up here. We actually need to turn that into a plus. Because if you go back and you look at how they were defined, it was m plus n. So really, if I turn this into a plus, that brings a minus sign in there, which then makes that a plus, and so everything is good. So it turns out that this one is exact, so we're going to be good to go. So that means we need to do two integrals. We need to do the integral of 2ty over t squared plus 1 minus 2t. And we're going to integrate that with respect to t. And then the other one we're going to integrate is the minus 2 plus the natural log of t squared plus 1 dy. So notice that I brought that minus sign in because it needs to be of the right form. All right, so far so good. Let's do the second one first because that's a little bit easier. Notice how all of this is constant in terms of y. So its integral is just going to be that times y. So minus 2y plus y times the natural log of t squared plus 1. And then I'm going to put plus some constant function in t. So whatever my potential function is, it's going to have minus 2y and then the y times natural log. Okay, now I go to the other side, and I need to integrate this one with respect to t. Well, the last part's pretty easy. Minus 2t is going to give me a minus t squared. And it's this other part that might be troubling, but notice that if I pull a y out, we've got y times 2t over t squared plus 1. And that is 100% a natural log form. U prime over u is a natural log form. So this gives me y times the natural log of t squared plus 1. And then I have to allow for some constant function of y. All right, so let's put it all together then. I'm going to have y times natural log of t squared plus 1 minus t squared, so I took care of those two pieces. I jump to my other one, I need a minus 2y. So there's my minus 2y. And then I need a y log t squared plus 1, I already got it. So there is all of that, and I just set that equal to c. So this example also shows something, another trick. If when you get to this point you're trying to integrate and one of the sides looks like really horrible to integrate, the other one's easy, do the easier one first. Because then you can do that same trick of, well, what if I differentiate this? What do I get? Oh, hey, look, it's this guy right here. You've already got it. Okay, so now let's get our c value. So we're going to plug in our numbers. We're going to let y equal 0 and t equal 5. And that gives us c equals minus 25. So when we put that all together, yeah, I'll put that all together just by making the sign minus 25. And there is our implicit form of the solution. This is one we actually could solve explicitly. It wouldn't be too terrible. Okay, so Everett, when you like, this is right. Is it right?
Yes.
What you have right?
Yeah.
Are you sure? Okay, so notice that, so that's still not right.
Everything else is the same.
Are you sure? Even that natural log piece?
Yes.
Are you sure?
What am I missing?
Can anyone help him out?
It's
What's
positive.
different between his natural log piece and my natural log piece?
One's positive, one's negative.
Yeah, your sign is off on that as well.
Sorry.
It should be a,
Two strong signs.
you have two wrong signs. Now, why did that happen? Can you guys see why those two pieces and whatever it did, why did the 2y and the y log bits?
I missed that.
Right, you didn't distribute that minus sign. So
Yeah, but I should have done that.
watch out for that. It's got to be exactly the right form, which is m plus n times y prime. Right? So it's very close, but you know, minus signs can make all the difference.
I see.
Trust me on that. Okay, so cool, right? If they are in exactly this form, they are exact differential equations, and we know exactly what to do. I'm trying to say exact or exactly as many times as possible. All right. So that's kind of nice, but they're not always this form, right? Go back to when you were doing conservative vector fields. It was awesome when a field was conservative. It's beautiful. You love that. But if they weren't conservative, you still had ways of dealing with them, right? When the my and the nx weren't equal, you still had ways of dealing with them. Well, we need to do the same thing here. We need to see if we can kind of apply the same approach, but to something that's not exact, and somehow make it exact. All right. Well, here comes a friend we've seen back in the past. So let me give you one that's not exact. Okay. And we can confirm this pretty easily, even though it's in the correct kind of form. So you're given this one, and you're told, find the solution to this because we need it so that our bridge doesn't collapse, Mr. Civil Engineer. By the way, those of you who want to be civil engineers, like that's the thought process you want with every one of your problems. If I don't do this right, the bridge collapses and people die. Because like that's kind of what happens with civil engineers. So now you're maybe like, ooh, I don't want to be a civil engineer. Electrical engineers do this right, or else people get killed from electric shocks. I don't know if that's true or not, but that's why, dude, that's why I'm a teacher. What happens if I do something wrong? You guys mock me. It lasts for about a minute or two, and then I move on. That's great. Anyway. All right, so let's check. Is this exact? Well, here's m. Here's n. So if I do an my, I get 3x plus 2y. If I do an nx, I get 2x plus y. They are not equal, which means there is no potential function, which means it's not exact. All right, so it would be really easy at this point just to say, fuck it, I'm not going any further. It's not exact, I don't want to do it. But you guys know that that's not how mathematicians think. Right? What's a mathematician do when they run into something like this?
It's pretty close.
They go,
Apply that
it's,
constant.
I mean, it's not that far off, and maybe there's some way I can make it exact. Because we really like, you know, I talk about how mathematicians are lazy. We're also sore losers. We don't like being told we can't do something. It's some defiance disorder, I'm certain, that is just permeates mathematicians, right? You can't take a square root of -1. Oh yeah? I can't? Watch me. I'm going to call it I. There you go. Right? Like, we just like to do that. Right? Well, this is no different. So what do we do if it's not exact? We're going to make it exact. Or at least we're going to try to make it exact. And the way we're going to try to make it exact is by doing what we did. No, do you remember what we did the very first time we tried to do a linear first order? Like what the trick we played? Because like you know how to do them now, right? You get your P, you get your G, you integrate your P, put E to that, that's your mu, and then you get 1 over mu, blah, 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 blah. But we made that mu. Do you remember what we called that mu? It had a name. It's okay if you don't remember. It's called the integrating factor. Because it's a factor, something we multiply so that we can now integrate. But the trick that we pulled with that is we just multiplied by mu. And then we went, okay, if this is going to work, what form does mu need to have? And it turned out it needed to be e to the integral of p. Okay, well, we're going to do exactly the same thing here. We're going to take one of these guys, and I'll do it generically on this board right here. We're going to take a generic one and just say, all right, let's multiply by a mu. And let's see if we can figure out what mu needs to be so that this thing that isn't exact turns into an exact. All right, so here's a generic, right? So we have m plus n times y prime. So what we're going to do is we're going to multiply by an integrating factor, like we've done before. So I'm just going to multiply both sides by mu. And mu is going to be a function. Our goal is to see what form does that function need to take for this to work out. Okay, so if we do that, then we've got mu times m plus mu times n times y prime equals 0. So again, our goal is for this now to be exact. And for this to be exact, I need the partials of those two little bits that I highlighted in orange to be equal. So I'm going to take a partial of the first one with respect to y. Well, it's product rule now. So I'm going to get mu y times m plus mu times my. So that's those two pieces. And then I take a partial, and I need to set that equal to the partial of the other one with respect to x. So again, product rule. So product rule with partials. So I'm just going to move stuff around a little bit. I want to bring everything to one side, first of all. So I'm going to have mu y times m minus mu x times n. And then the other parts, I'm going to pull out the mu. I can factor it out. So just a little bit of algebra gets me here. Okay, so whatever mu is, it's got to satisfy that. Okay, still similarly yuck, right? So here's what we're going to do. Let's make an assumption. We can talk about the validity of this for sure. But let's just do this. Let's assume that mu is only a function of x. Now, it may not be, right? 100% may not be. So maybe assume isn't the right word. Maybe this is like case number one. Let's look at the first case where mu is only a function of x. Because then we're going to look at, well, what if it's only a function of y? Right? But let's just assume that this is true. So then, we know mu y equals 0. Because if it's only a function of x, we differentiate with respect to y, it goes away, whatever. Right? So that's going to be gone. Well, then if we kind of look at this, if mu is only a function of x, then this mu sub x is really just mu prime. And so this turns into minus mu prime plus mu times my minus nx equals 0. You recognize that form? Classify that differential equation. What order? First, because there's prime. Is it linear?
Yes.
Yep. Hey, this is linear first order. Oh shoot, there's an n. But this is linear first order. Let me rewrite it so that it looks like linear first order. So it's linear first order, and even better, it's homogeneous. It's equal to 0. We already know how to solve these. So if we get into this situation where mu is only in terms of x, then mu is going to equal e to the integral of my minus nx over n. That's what you get when you separate it, do the linear first order stuff. I'm not going to bother doing all that because I already know you know how to do it. but that's what that mu ends up equaling. All right, so that's kind of nice, honestly. But also think about this. If mu is only a function of x, that means this fraction has to be only in terms of x. Because if there are y's in there, then this is a function of x and y. Which means this piece right here needs to be only x's. So for this assumption to be the case, where mu is a function of x, that thing has to be only x. If it's not only x, this is a bad assumption. Okay, so the question then goes, well, what if mu is only a function of y? Well, let me just change the color. So if mu is only a function of y, then mu x equals 0. Which means instead of having an n on this, we've got an m on it. And that leads to a mu prime plus my minus nx over m times mu equals 0. So notice that it's a pretty similar form. It's just over m instead of n. And if this is the case, then we can get a mu for this one as well. And the mu is e to the negative integral of my minus nx over m. And it's only a minus sign because of the fact that this is a different sign. There should be a dy on that. So similarly, this is only going to work if this fraction right here is only y, no x. All right, so this is how we're going to attack these. If they are not exact, if one of these two fractions is only in terms of one letter, we can use that to create a mu to multiply and make this thing exact. So all of this stuff, I know, like, your brains are scrambled. I know. Let's put it into action so you can see how it's used. But it's really, we just look at these two forms. So you always start with my minus nx. Remember that in vector calc? If you don't have a conservative vector field, you got to go to that theorem about finding the closed path integral by looking at the double integral over the area that you're inside. And do you remember what you integrated in that integral? The difference in those two partials. So there are a lot of connections between this and what you did with vector fields. Okay, well, let's just start there. Let's go with my. So we've got this example. Let's see what happens when we do my minus nx. So that's 3x plus 2y minus 2x minus y, which is x plus y. So if we are going to be able to attack this one using an integrating factor, we have to be able to take that x plus y and divide it by either m or n and get only a function of x or a function of y. Okay, let's just check them both real quick. So if we do the my minus nx over m, so that's x plus y over 3xy plus y squared. I don't know about you, but I don't really see that getting rid of one of the letters. If I look at the other one, So that's going to be x plus y over x squared plus xy. Check that one out. Factor on the bottom. You can factor out an x. So those x plus y's cancel. And we're left with 1 over x. Hey Jackson, can you check, make sure that that's in field of view on the camera?
Yes.
You can see that? Okay, cool, thank you. All right. So, let's take a look at that guy real quick. All right, don't change my angle too much. All right. Now, for that one, if we kind of come back and look, my minus nx over n has to be only a function of x. Yeah, it is. It's only a function of x. So we found the one that we can use. We need to use this guy. So the mu we're going to pick, so this one doesn't work, that one does. So the mu is going to equal e to the integral of that value. Okay, so the integral of 1 over x is natural log of x. E to the natural log of x, of course, is just x. Okay, so we just did a whole bunch of work. Just to find what we multiply to everything to make it exact. So we're going to come up here and we're going to take both sides of this equation and multiply by x. So we now have 3x squared y plus xy squared plus x cubed plus x squared y times y prime equals 0. And this one is now exact. You can check it with the partials, or you can just take my word for it. Which means now that it's exact, let's get ourselves a potential function and be done with it. So I'm going to integrate the first bit with respect to x. So that's going to give me an x cubed y. The second part with respect to x is going to give me a x squared y squared over 2. So those two pieces with respect to x. Then I go to the next part and integrate with respect to y. Well, x cubed gives me x cubed y. It's already there. X squared y, if I integrate that, I get x squared y squared over 2. X squared y squared over 2. And then I fire on my C. All right, so there is our general solution to this differential equation in implicit form. This one we can solve explicitly. Like if we had an initial value, plug it in, find our C, we can solve this explicitly. It's going to be a quadratic in y. It's going to be horribly ugly, but we can do it. When that happens, we're going to get a plus or minus. The plus or minus will be determined by our initial value once we're there. So these, again, are not exact, but they can be made exact just by doing one little kind of tweak. All right. Let's just pause for a second here. No doubt about it, these are rough, right? Because think about what you have to do. First of all, you got to make sure you're in this form, and everything can be written in this form, so yay. But when it's in that form, first you have to check, do the partials match? If they do, it's pretty fast, right? But regardless, even if they don't, like in the situation where they don't, then we have to look at the two different combinations, see if one of those is just a function of x or y. If it is, then we got to find our mu, doing the e to the integral of all the garbage. Then we're going to take that, multiply it through, and now that we've got that exact, Now we have to integrate again. Once with respect to x, once with respect to y, fuse those together. And so there are a lot of steps, right? There are a ton of steps to these, but there's a recipe. There's a recipe. It's the same steps every time. Same steps every time, which makes it better. It really does. Because think about, like, you guys bitch and moan about proofs all the time, right? From linear. Why were those horrible? Because they're all different. There is no recipe. You got to think about all the different things that maybe you can use and blah, 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 blah. Right? How bad is RREF? Even without a computer, how bad is it?
Pretty chill.
I mean, it's worse, but it's not as bad. Because why? There's a recipe. You do it the same way every time. Right? And we are, what, in week 3 now of differential equations? Everything we've done is a recipe. Every single one of them. Right? Like, if we wanted to, we could actually make a recipe book for differential equations. I mean, that's what a textbook kind of is, right? But each one of them has a recipe. We did just a little card. Oh, you want to make an exact? Here's your recipe for exact.
And for these, it looks like you can do like pretty much any first order like this, right? Is there a time when you can't?
Yes. In order for us to do this, it comes down to these guys.
Oh, okay.
If those are not just single variable, this process won't work.
Got it.
So it's at least a method that you can attempt for any first order. But will it always work? No. It really is going to end up depending upon what M and N look like and how those things kind of, how these two play out. Okay, because, so these, you notice how I said, let's assume it's only a function of x and then only a function of y. The case that we haven't dealt with is, what if that resulting thing is a function of both? What do you do?
Not this.
Not this method. Yeah, and that's pretty much how all of these things have played out, right? Like, what if it's not linear first order? Can you use linear first order methods? No. Does it mean you can't solve it? No, you just have to use different methods. Oh, check it out, it's separable. Cool, so we'll separate. Oh no, this one's not separable, nor is it linear first order, but it's exact, right? So it's kind of the goal of all differential equations is, here are all the different kinds of equations you might have. We want to be able to sort them into groups and go, okay, this group, I know how to solve these. I've got a recipe for handling these. Now all the rest, let me group these guys together. I've got a recipe for solving these. And that's basically what we've been doing these first couple of weeks, is taking these first orders and bundling them into groups. What groups do we have right now? What methods do you know? So linear. So linear is a nice big group. And it's beautiful. Anything in that group, recipe, done.
Separable.
Separable. There's a recipe, although that one, once you separate, you got to integrate what's left with all those y's and x's. Easier said than done, but there's a process. Okay, what else? So autonomous. Autonomous really are separable. They're like a smaller pile within the separable.
I said homogeneous.
Oh, homogeneous. I'm sorry. Yeah. So.
I didn't even know that one.
Oh, okay, I apologize. So then there were, and do you mean like homogeneous or homogeneous or?
Oh.
Yeah, okay. So we've got like those special forms, right? So like the one that can be written as a function of y over x, and then the Bernoullis are another, right? So it's like, okay, so then here's the y over x ones, and here's the Bernoulli ones. Now we got exact ones, and then we've got the almost exact but needing an integrating factor ones. Right? And so we're just grabbing all these different equations and throwing them into one of the boxes. Because each of those boxes has a recipe, has a way to actually do Okay, but those recipes are those recipes. And obviously if integration is tricky, every one of these is going to be problematic because they're all integration. Every single one of these things involves integration. And always will. Right? And so I'm going to imagine as you're playing around with them, that's going to be the biggest hang up. Once you get them classified, right? Once you figure out which box they belong to, that might actually be the hardest at the beginning, is trying to figure out, okay, which of these forms is this guy? Is it exact? Is it linear first order? Is it, and sometimes they fit in multiple boxes. That's the other problem, right? We've seen a bunch that, oh, hey, look, it's separable and it's linear first order. Oh, it's linear first order and it's exact. And it's separable. And well, in that case, pick your favorite. Right? Pick your favorite method, whichever one you're most comfortable with. All right, so I know that's a lot. We'll go ahead and call it for today. I know your brains have gotten quite the workout. But on Wednesday, we'll start applying this stuff. I think we're at the point where we want to start seeing why we give a shit about this. Because right now, that's probably really abstract, right? Because all we've been doing is just practice and practice and practice. So starting Wednesday, I'll start showing you why we care. Okay?